What exactly is time? That's quite a challenging question, isn't it? We all have this sense that we understand time because we live through it constantly. The constant march of seconds, minutes, hours. But here's the extraordinary insight that Einstein uncovered. Time isn't uniform for everyone. Time isn't this fixed entity that advances at an identical pace throughout the entire cosmos. That's what Newton believed. And it appears obvious, doesn't it? Yet it's incorrect. Allow me to share an illustration. Picture owning a timepiece. Not an elaborate one, merely the most basic timepiece you can imagine. It consists of two reflective surfaces, one positioned above, one positioned below, and a solitary particle of light rebounding between them. Each occasion, the light strikes the lower surface that marks one click. Each occasion, it strikes the upper surface that marks one talk. Straightforward, correct? Now, if this timepiece sits directly before you, stationary, you observe the light travel straight upward, rebound, descend straight down, rebound. The duration between clicks equals simply the gap between the surfaces divided by light's velocity. Let's designate that gap as d. So the duration for one complete click-talk cycle equals 2d divided by c, where c represents light's velocity. Nothing complicated thus far. But now here's where it becomes fascinating. Suppose I take that timepiece and I place it aboard a spacecraft, and that spacecraft begins moving, not merely drifting along, but truly moving at a considerable portion of light's velocity. Now you remain stationary watching the spacecraft race past you, carrying this timepiece. From your viewpoint, what path does the light follow? Well, the spacecraft is in motion. So by the moment the light travels upward to the upper surface, the entire spacecraft is shifted sideways somewhat. The light doesn't merely travel straight upward anymore. It travels upward and sideways. Then when it returns downward, the spacecraft has shifted further, so it travels downward and sideways. The light traces a zigzagging route. Now here's the essential point. Light's velocity remains constant, always constant. This represents the most significant experimental finding across all physics. Regardless of your speed, regardless of the source's speed, light always moves at precisely the same velocity, roughly 300,000 kilometers slashes, not 300 roll 1, not 299,999. Precisely identical. So if the light must traverse this extended, zigzagging route while moving at the identical velocity as before, it must require more time to finish one click-talk sequence. It must. The route is extended, the velocity matches, therefore the duration must be extended. This involves geometry. This involves simply the Pythagorean theorem. You can calculate it using basic mathematics. What does this indicate? It indicates the timepiece aboard the spacecraft clicks more slowly than the timepiece resting here with you. But consider this. It's not a defective timepiece. It's the identical mechanism. And here's the genuinely astonishing aspect. Everything aboard that spacecraft operates slowly. Not merely this light-based timepiece. Every timepiece, mechanical ones, digital ones, atomic ones, your pulse, your thinking, chemical processes, everything. Time itself passes more slowly aboard that spacecraft. Now, you might protest. Hold on, that's absurd. Surely the individual aboard the spacecraft would detect their time passing slowly. But no, you see, that's the elegant aspect. From the spacecraft's perspective, they're not moving whatsoever. They're simply resting there. You're the one moving past them. So from their perspective, their timepiece clicks normally, and your timepiece clicks slowly. And they're accurate. Both perspectives are accurate. That's what makes this so peculiar. No inconsistency exists here because you cannot directly compare your timepieces unless you reunite them. And when you calculate what occurs when they reunite, accounting for the speeding up and slowing down, you discover that the moving timepiece genuinely has recorded less duration. The traveling twin genuinely is younger. This isn't philosophical speculation. This isn't merely theoretical discussion. We've verified this using precise timepieces aboard aircraft. We observe this constantly with particles and accelerators that exist longer than expected because they move so rapidly that time decelerates for them. Allow me to present the actual equation because I believe mathematical expressions can be elegant when you comprehend their meaning. If you're moving at some speed v, and I measure a time span of t on my stationary timepiece, then you, on your moving timepiece, will measure a time span of t multiplied by the square root of 1 minus v squared divided by squared. That square root factor, we designate it the Lorentz factor. It appears throughout relativity theory. Let me express it clearly for you. Gamma equals 1 divided by the square root of 1 minus v squared over c squared. That's the expression. That's the factor by which time decelerates. Now let's examine this expression carefully. When you're moving slowly compared to light, v is much, much smaller than c. So v squared divided by square approaches 0. The square root of 1 minus nearly 0 approaches 1. 1 divided by nearly 1 approaches 1. So gamma approaches 1, and time passes nearly normally. That's why we don't perceive this in ordinary existence. Even a jet aircraft traveling 1,000 kilometers per hour only moves at about 1/1,000,000th of light's velocity. The time alteration is extraordinarily tiny. But as you accelerate, as v approaches closer and closer to c, observe what occurs to that expression. The ratio v over c approaches 1, so v squared over c approaches 1. So 1 minus v squared over c squared approaches 0. You're taking the square root of something approaching closer and closer to 0, which itself approaches closer and closer to 0, and then you're dividing 1 by that 1 divided by a number approaching 0, expands larger and larger and larger without bound. Allow me to provide some figures to make this tangible. At 10% of light's velocity, relatively slow by cosmic measures, time passes about 0.5% slower. You wouldn't perceive that unless you possessed an extremely precise timepiece. At 50% of light's velocity, time passes about 15% slower. Now you notice if you spend a year traveling at that speed, people back home would age about 14 months. At 90% of light's velocity, time passes less than half as fast. 1 year for you, exceeding 2 years for them. At 99% of light's velocity, time passes at about 1/7 speed. 1 year for you, 7 years for them. At 99.9% of light's velocity, about 1/22nd. At 99.99% of light's velocity, about 1/70th. You perceive where this leads? The closer you approach light's velocity, the more dramatic it becomes. And we've verified this at the CERN laboratory in Europe. They've accelerated electrons to 99.999% of light's velocity. That represents 6 nines. At that speed, the time alteration factor exceeds 2,000. A particle that normally exists for 1 microsecond will exist for 2,000ths of a second. We observe this. This represents reality. Now, here's where it becomes genuinely bizarre. What occurs precisely at light's velocity? What occurs when v equals c? Let's examine that expression again. If v equals c, then v squared divided by square equals 1. 1 minus 1 equals 0. The square root of 0 equals 0. 1 divided by 0 is, well, it's not a numerical value. It's undefined. It's infinite. What does this signify? It signifies time alteration becomes infinite. Time doesn't merely decelerate. It halts. It freezes from the perspective of something traveling at light's velocity. No time passes whatsoever. Consider a photon, a light particle. It originates in the sun's interior. It bounces around for perhaps 100,000 years, working its way to the surface. Then it travels through space for 8 minutes and reaches your eye. From your perspective, that photon has been traveling for 8 minutes. But from the photon's perspective, no time has elapsed. 0. The instant it was released matches the instant it was absorbed. Its complete journey from formation to absorption occurs in a single moment of its own time. And there's more. Just as time expands, distances compress in the movement direction by the identical factor. At light's velocity, distances shrink to 0, so that photon doesn't merely experience 0 time, it experiences 0 distance. From its perspective, the sun and your eye occupy the identical location. The entire cosmos in its travel direction is compressed completely flat. No thickness whatsoever. Now, I must exercise some caution here because technically we cannot establish a reference framework for a photon. Einstein's equations don't function precisely at light's velocity. You cannot perform a Lorentz transformation with v equaling c. The mathematics fails. But we can examine what occurs as we approach closer and closer to light's velocity, and then we can observe what it approaches. And what it approaches represents 0 time and 0 distance. This explains why nothing possessing mass can travel at light's velocity. Observe what else occurs as you accelerate. Your energy increases. In fact, your energy equals your mass multiplied by light's velocity squared multiplied by that identical Lorentz factor. As you approach light's velocity, the Lorentz factor approaches infinity. So your energy approaches infinity. It would require infinite energy to accelerate you to light's velocity. The universe doesn't possess infinite energy to provide you. Only entities with zero mass, like photons, can travel at light's velocity. And they must travel at light's velocity. They cannot travel slower. They cannot travel faster. They can only travel precisely at c. Allow me to share something I find absolutely elegant about this. The fact that time halts at light's velocity isn't merely some peculiar oddity of the equations. It's profoundly connected to the fundamental structure of the universe. Space and time aren't separate entities. They're interwoven into what we designate spacetime. And light's velocity isn't merely the speed of light. It's the conversion factor between space and time. It's the speed at which causality propagates. It's the maximum speed at which information can travel. When you move through space, you rotate your path through spacetime. The faster you move through space, the slower you move through time. A trade-off exists. You're always moving through spacetime at the identical total rate, but you can allocate that movement between the space component and the time component in various ways. When you're stationary in space, all your movement occurs through time. When you move through space, you exchange some of that time movement for space movement. And when you're moving at light's velocity, all your movement occurs through space, and none occurs through time. Here's another perspective to consider. In our everyday experience, we perceive space as having 3 dimensions and time as being separate. But relativity informs us that's not entirely accurate. Time represents a 4th dimension, yet it's a special type of dimension. It carries a negative sign before it. In the mathematics, when you calculate the interval between 2 events in space-time, you take the square root of the time difference squared minus the space difference squared. That negative sign proves essential. Because of that negative sign, 3 categories of separations exist between events. If the time difference exceeds, we designate it time-like. You could travel between those events slower than light. If the space difference exceeds, we designate it space-like. No information can connect those events. They lie outside each other's light boundaries. And if they're precisely equal, we designate it light-like or null. Only light can connect those events. At light's velocity, the space-time interval equals 0. From the photon's perspective, the emission event and the absorption event exhibit 0 separation in space-time. They represent the identical event. This carries some rather profound implications. We discussed the universe's age, correct? Approximately 13.8 billion years. But that represents the age in our reference framework, moving slowly through space. For photons that have been traveling since the Big Bang, no time has passed whatsoever. They were created and they continue existing all within the same timeless moment. In a sense, for light, the Big Bang continues occurring. The complete history of the universe from beginning to conclusion compresses into a single instant. Now, you might inquire, if time halts for photons, how can they possess frequency? How can red light differ from blue light? That's an excellent inquiry. The answer indicates that frequency isn't something the photon experiences. It's something we experience when we detect the photon. The frequency depends on our reference framework. If we're moving toward the source, we detect higher frequency, blue shifted. If we're moving away, we detect lower frequency, red shifted. The photon doesn't possess frequency in its own framework because it doesn't possess its own framework. Allow me to provide one additional example to demonstrate how strange this becomes. Cosmic rays consist of particles arriving from space, and some of these particles are called muons. Muons are unstable. On average, a muon exists for about 2 microseconds before it disintegrates, 2 millionths of a second. Then it vanishes. Now, these cosmic ray muons form high in the atmosphere, perhaps 10 kilometers up, and they're traveling extremely close to light's velocity, say 99.8% of c. Even at that remarkable speed, it should require about 33 microseconds for them to reach the ground. But they only exist for 2 microseconds, so they should all disintegrate before arriving here, yet they don't. We detect numerous at ground level. Why? Time alteration. At 99.8% of light's velocity, the time alteration factor approximates 16. So while 33 microseconds pass for us, only about 2 microseconds pass for the muon. From the muon's perspective, it experiences its normal existence duration and just reaches the ground. From our perspective, it experiences 16 times longer than normal and reaches the ground. Identical outcome, different explanations. Or you could examine it from the muon's viewpoint using length compression. From the muon's perspective, it's not moving. The Earth moves toward it. And because the Earth moves at 99.8% of c, the 10 kilometers of atmosphere compresses by a factor of 16 down to approximately 600 meters. So even though the muon only exists 2 microseconds, and even though light only travels 600 meters during that duration, that suffices because the atmosphere only measures 600 meters thick from the muon's perspective. 2 different methods of examining it, both accurate, both yielding the identical result. That's what I appreciate about physics. When you genuinely comprehend it, all the components interconnect. So why does the universe freeze at light's velocity? Because that's how space-time is structured. Light's velocity is embedded within the universe's geometry. It represents the maximum speed of causality. It's the conversion factor between space and time. And because of the particular mathematical structure of space-time, featuring that negative sign in the metric, when you attain that speed, your time halts and your space collapses. It's not that something magical occurs at 300,000 kilometers / it's that a fundamental speed limit exists embedded within reality structure, and light happens to travel at that speed because photons possess no mass. If we inhabited a different universe with different physics, the numerical value might differ, but the principle would remain identical. A maximum speed would still exist, and at that speed, time would still halt. You know, when I initially learned about this as a student, it troubled me. It appeared impossible. How can time differ for different observers? How can everyone be accurate? But the more I contemplated it, the more I understood that this actually represents the sole way it could be, given that light's velocity remains constant for everyone. Once you accept that single experimental finding that light always travels at c regardless of your movement speed, everything else follows through pure reasoning. Time alteration isn't mysterious, it's unavoidable. And that's what I want you to retain from this. The universe isn't obligated to conform to our everyday intuition. Our intuition developed to handle objects moving at human speeds, meters per second, perhaps kilometers per hour. We never developed to handle objects moving at 300,000 kilometers per second, so naturally, it appears strange, yet it's not strange. It's simply different from what we're accustomed to. The universe freezes at light's velocity because that's what the universe does. That's how space-time functions. And once you accept that, once you genuinely comprehend it, you begin to perceive that it's actually quite elegant. Time and space aren't separate, they're facets of the identical entity. And light's velocity represents the exchange rate between them. Every photon entering your eye at this moment from the sun, or from a distant star, or from the light fixture above you experiences no time during its journey. For that photon, its formation and absorption occur simultaneously. The entire voyage from its perspective occurs instantaneously, yet from your perspective, it traveled for seconds or years or millennia. Both perspectives are accurate. Both represent equally valid descriptions of reality. That's relativity. That's time's nature. And that's why at light's velocity, the universe freezes. Not because time constitutes an illusion, but because time proves flexible. It's relative. It depends on your movement speed through space. And isn't that remarkable?